Alright, cool. So let's get started. So question 1. This is a gas chromatography. First of all, you see is the absorption. They give you different peaks because they separate out, okay? So they separate out the aldehyde, alkane, and carboxylic acid, and they are observed at different times. So this is observed the fastest. It's observed at just under 5 minutes. This was observed at around 10 minutes. So this one was observed around 15 minutes. Okay, the time there refer to something called retention time. The definition of retention time, you gotta know. Okay, I'm not sure if they ask you in this question or not, because sometimes they do, but you gotta know the definition of retention time. Yeah, okay. So Z pass through the gas chromatograph the slowest. That's why it comes out the slowest. Okay, you gotta know about the principles of gas chromatography. Yeah, how does it work? Well, it actually tells you, lucky for you, it depends on their solubility in the stationary phase. The stationary phase is a liquid alcohol. So these things don't move. These things move. They pass through the chromatography machine and then they get separated based on their relative solubility in the stationary phase. Something that will be soluble in liquid alcohol means that you will stay around longer. Okay, why? Because this is the thing that doesn't move. It is polar. So that means the most polar substance would stick to this, would be more attracted to the stationary phase which doesn't move, and therefore eventually it will move the slowest. So what we can establish is this is going to be the most polar. How do I know that? Because the stationary phase is a liquid alcohol, is also polar. So the more polar the substance, the more they would like to stay around and interact with the liquid alcohol. Okay, and this will be the least polar. Well, between the alkane, aldehyde, and carboxylic acid, I hope you can appreciate that X has to be the alkane, which in that case it has to be the alkane. And between aldehyde and carboxylic acid, I hope you can appreciate that carboxylic acid can form hydrogen bond, whereas aldehyde only can form permanent dipoles. So hydrogen bond with the liquid alcohol is gonna be stronger. So this will be the carboxylic acid. And obviously this leaves the middle thing being aldehyde. And then I need to reference to relative to the molecular forces of the compound. So alkane is non-polar. So only forms weak van der Waals, force of attraction to the polar stationary phase, which is a liquid alcohol. Stationary phase, which is an alcohol, as it is told in the question. Yeah, stationary phase, the thing that doesn't move, is liquid alcohol. Okay. Now aldehyde, you have the delta minus there and the delta plus. So this one can form permanent dipole. So the CO bond of aldehyde is highly polar. So we're talking about the bond itself. Therefore, can form permanent dipole. Can form permanent dipole. And hydrogen bond. In fact, hydrogen bond is possible because you have the liquid alcohol, so you have the OH of the alcohol, delta plus then. So yes, this thing that cannot form a hydrogen bond between aldehyde and aldehyde, but this is a stationary phase. It's got liquid alcohol, it's got OH there, so that thing can form hydrogen bond with this thing there. So you can form hydrogen bond with the alcohol of the carboxylic acid and hydrogen bond with the stationary phase. So I've just outlined all of them. It's not just permanent dipole, it's also hydrogen bond as well, right? Okay. Obviously, carboxylic acid has the same deal as well, but hydrogen bond is easier to see. Okay, so the most polar molecule. So the OH and the C double bond O of carboxylic acid can form H bond with the alcohol of the stationary phase. So therefore making it very soluble in the stationary phase, right? So therefore it stays around in the stationary phase longer. That's why the retention time is higher. That's why it comes out and becomes detected at a much longer time from the start of the experiment. Okay. Next bit, you gotta know that it's the area that you're interested in for Z. So that is 47, and then you sum up the area under the graph. So that's just that. You multiply by 100%. It's going to 47.959. It's roughly 48% then. There's 2 sig fig. Based on the data given, they are all 2 sig fig. They don't mention what is appropriate. Appropriate comes down to whether you are aware of the precision of the data given or not. All right. Oh, this bit is on thin layer chromatography, also short form is called TLC. So you gotta use your ruler. Identify. Not really, no. They have similar molecular masses, J, K, and L. Any other information? Oh yeah, this is the information. The stationary phase is polar. The mobile phase is non-polar. That is the most important thing. Moving. What is moving? The mobile phase is non-polar. So out of all three, you will have J being the ketone and the carboxylic acid. K is ethane dioic acid. And L is CH3, CH2, CO, CH2, CH3. Is that correct? No, that's not correct. One extra carbon. CH3, CH2, C double bond O, CH2, CH3. Okay. I hope you can see there's 2 times carboxylic acid and 1 time carboxylic acid and no carboxylic acid. Okay. So the more the carboxylic acid groups there are, i.e. 2 in K, 1 in J, 0 in L, therefore can form hydrogen bond. But you see, your moving phase is non-polar, okay? But mobile phase is non-polar, so least likely to form H bond is going to be least polar, therefore move faster. It's the opposite story. If your mobile phase is polar, then the one which is more polar will move faster. But here, your mobile phase is non-polar, so that means the least polar molecule will move faster. Out of all of these, the least polar is going to be the one that forms no hydrogen bond, because when you have the hydroxyl, you can form hydrogen bond with the polar stationary surface. So L is going to move the fastest. L is 1. 2 carboxylic acid versus 1 carboxylic acid. K is going to move the slowest, and J is going to move somewhere in the middle. So that's 2, 3, 1. Okay, so well, RF value is a ratio. Okay, so it's the distance traveled by the compound or your component from your baseline. Your baseline is the line you draw with your ruler. This is your baseline where you spot the mixture, and then the solvent front, so the distance moved by the solvent divided by the distance traveled by the solvent, basically to the solvent front. Okay, it stands for retention factor. But just by stating what is retention factor, really, it doesn't really help to explain it, right? So basically, the RF value for 3 is going to be the distance over the total distance to the solvent front. RF value for 2 is this distance to the solvent front. Okay, it's a ratio. Now you want two different bonds that are responsible for the infrared. Okay, infrared. So, well, you can obviously think about the aldehyde and the OH bond. The rest are the same, all right? So two different bonds, C double bond O and then the OH, okay? So the C double bond O, if you look in the data booklet, this will give you 1670. By the way, this is of an aldehyde, so you need to choose the right one, which is for aldehyde, okay? So 1670 to 1740. And again, this is the OH, but it's of an alcohol, not a carboxylic acid. It's for an alcohol. So make sure you choose the right range of values, yeah, from the data booklet. All right, so pretty straightforward there. So now they want you to use the data booklet to see how the infrared would would differ from each other. Well, first of all, what is different? This is different. This is different. This is different. This is different. Okay. So there are two differences here. Oh no, hang on. When you say this is an OH, this is also an OH. So you can't really use the OH as your difference. All right. But you cannot say NH is not present because you also have an NH. Infrared really tells you the difference in bond. Infrared does not tell you functional group. Infrared tells you bond. Okay. So in M, there is a carbonyl, CO stretch at, well, it's a CO of a carboxylic acid. So if I have a look at my data booklet, where's my data booklet? So inside the data booklet on infrared, the CO of a carboxylic acid is at 1680 to 1730 cm minus 1. These are strong. These are strong. This will be sharp because it's not OH bond. Okay, it's strong, sharp absorption, which will be present in M, absent in serotonin, because serotonin do not have a carbonyl CO stretch. You cannot use the OH because this one has the OH as well. You cannot use the NH because this one has the NH as well. Okay, despite this NH missing. This is the infrared spectrum of glycer, which is what you have just drawn. As you could see, these are pretty broad, this region. So this is broad, strong, broad absorption. Not too surprisingly, there's our OH bond. Infrared tells you about bonds, not about functional groups. We have a carbonyl, C double bond O there. So it makes sense that we have a carbonyl around this region, C double bond O. And this C double bond O is not of a ketone aldehyde, it's of an amide, C double bond O, NH. Peptide is an amide. Amide is not always a peptide. Be very careful, yeah? So this is a C double bond O. This is of an amide. Infrared does not tell you functional group, but I know the functional group because from here. Okay, the OH here refers to the carboxylic acid as well as the alcohol. So this is also alcohol, which you get from the side chain, and of course the carboxylic acid, which you get from, well, this carbon terminus of the one of the amino acids there. Okay. What do they want? They just want the bond, so be very careful. They don't want functional group, so this is not a functional group. As I mentioned earlier, infrared tells you bond, not the functional group. So there's the OH there, and the F is the C double bond O. What is this G here? Let's have a look on the data booklet in infrared region. What do we have? We are looking at amide. Amide NH is pretty high, 3300 3500. This is pretty low, around 1000. So we have a C double bond O alcohol, so that looks about whatever that fit here. So this is alcohols or ether or esters, blah 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 blah, but all that are wrong because you do not have esters, you do have alcohol. You have an amide, but you do have alcohol, which is C single bond O. So there is around 1000 wave number, Cm-1. So there is C double bond O. So that's very clearly quite an obvious one there for that 2 marks. And that's the end of that question. Cool. So this question, first question is about a gas chromatography. So you should know the principles of gas chromatography. It's a separation technique. Okay, so you could separate this alkene, carboxylic acid, and ketone. The thing is they are of similar volatility, so they have similar boiling point. Otherwise, you could have used distillation, fractional distillation to separate them when they have very different boiling point. But because they have similar boiling point, then it's very hard to separate them. So you can use gas chromatography in this case. So they tell you how the concept works, although you should know how it works anyway. So chromatography has two phases. One is stationary phase, that means it's not moving. The other one is the mobile phase, that's the one that's moving. Okay, the ability to separate these three compounds depend on their relative solubility in the liquid stationary phase. So you have a liquid stationary phase, which is an alkane. An alkane is non-polar. Okay, it's a non-polar hydrocarbon. So hydrocarbon contains only carbon and hydrogen atoms. That is your O-level definition there. So you can't complete the table to suggest which compound in the mixture is responsible for each peak. You need to refer to the intermolecular forces present in each compound. This is the thing that is not moving in the column, stationary, not moving. It's non-polar. So you expect that non-polar would like the most to interact with non-polar stuff. This is non-polar alkene, also hydrocarbon, right? So non-polar as well. So this is the one that's going to interact the most with this non-polar stationary phase. So this is the one that's going to stick around much longer in the liquid stationary phase. So this is going to be the one that's going to be detected the last, because it's the one that favors the interaction with the non-polar the most, because this is polar and ketone also has polar. In terms of carboxylic acid, you also can form hydrogen bond, because not only you have the C double bond or carbonyl, you also have the OH which can form hydrogen bond. Okay, but obviously like they form hydrogen bond between themselves, but there's nothing on here, the non-moving liquid stationary phase. There's nothing here that can form hydrogen bond to this. So this is not going to like this at all, okay, because this is the most polar compared to ketone, which just has permanent dipole. Okay, because you only have the C double bond O. There's no hydrogen bond there because there's no hydrogen bonded to F, N, or O. That's your definition of hydrogen bond. Yeah, you gotta know, not just because you have oxygen then you have hydrogen bond. No, yeah, okay, you gotta have a hydrogen first of all bonded to a very highly electronegative element. Okay, and there's a second condition as well, which I leave you to go back to AS to find out. Yeah, so in terms of the alkene, oops, I forgot. So this is going to be the alkene, because it's the most non-polar. And then we can say this is the carboxylic acid compared to the ketone, because this is the most polar. Therefore, it wouldn't want to linger around, it wouldn't want to stick around to the liquid stationary phase. It would just prefer to pass through the column just like that, and it will be detected the earliest. It has the shortest retention time. Okay, so meaning to say J is not an alkene. J is going to be the carboxylic acid. K is the ketone, and then the one which is detected the last, that's going to be the alkene. Not an alkane, be careful. The liquid stationary phase is alkane, but here is specified as alkene, which you will have read the question anyway. Okay, now you got to refer to the intermolecular forces, right? So carboxylic acid can form carboxylic acid is the most polar of the three substances. It is least likely to linger or to dissolve in liquid stationary phase, which is, oh sorry, I don't think I mentioned the intermolecular force here. Yeah? Okay, it's the most polar of the three, can form hydrogen bond, due to OH. But alkane stationary phase is non-polar, so it wouldn't stick around. Yeah, okay, so ketone can form permanent dipole. okay, between themselves. So obviously the carboxylic acid can form hydrogen bond between themselves, but not to the stationary phase. Okay, so it doesn't dissolve in the alkane. Weaker than hydrogen bond. So it doesn't have hydrogen bond, which is absent here. Won't interact much with nonpolar alkane. Now you have the nonpolar alkene will interact most favorably, meaning most likely to interact with nonpolar alkane stationary phase, but I haven't specified what kind of interaction here, by forming van der Waals or by having van der Waals forces of attraction between them. So it's going to be the more soluble in the liquid stationary phase, therefore it's going to stick around much longer in the column. Okay, now next bit is about area under the graph. So what happened is you want for K, right? So the percentage by mass for K is going to be the area of K divided by the sum of the area. But you want percentage, so you're going to multiply by 100%. So put that into your calculator and you should get 19.565. By looking at all the data given, these are all too sigfig. So appropriate is going to be 20%. Okay, that is to 2 sigfig percent. Okay, so that's 2 sigfig.